Hello and welcome to my presentation where I'll be teaching about the fluxes in the Arctic. So firstly, we need to consider the water circulation within the Arctic. So this is a small cartoon that shows the different water systems in the Arctic Circle. Firstly, we'll consider the surface circulation systems. So we have the Berthold Grai, which occurs just off the coast of Canada, near Alaska as well. And it is an anticyclonic motion that carries both seawater and sea ice. Accompanying that, we have the transpolar current, which carries water from different regions within the Arctic Circle, but mainly from the Leptive Sea all the way down to the Fram Strait, and then eventually passing onto a system that passes water through the Greenland Sea, past Iceland, and so on. Now, accompanied with that, we have the deep circulation systems. So firstly, we have the cyclonic circulation. This occurs at greater depths, and it helps to protect the sea ice from the Atlantic water heat. Now you might be thinking, where does this Atlantic water heat come from? And the answer to that is it originally comes from the North Atlantic current, which carries water from the subtropics all the way up, and then it eventually dives under and provides water to that cyclonic circulation. The water is then mixed between the surface and the deep ocean by ocean mixing mechanisms. Momentum transfer. So this is a small diagram which just shows the different components of the sea ice and then also the seawater. So momentum is transferred to the surface level ocean via different interactions with the seawater and the sea ice. Now, what are the interactions? It's actually the wind. The wind will come along and pass through, and then in doing so, it will transfer momentum. Now, the amount of momentum that is applied is simply the mass of the wind times the velocity. However, there are some different intricacies we need to consider. So for the seawater, the amount of momentum transfer depends on factors such as coefficients, shape of wave, and then the velocity. It actually gets more complex when considering the sea ice due to ice fragmentation and then also the friction between the ice and the wind. The ice is actually a lot more smooth than the seawater. That's something to consider for later on. So a question. So, an area of research that has been very prominent in recent years is will reduced sea ice coverage affect ocean mixing? Now, what I can say is that the seawater, having an increased amount of seawater will increase the rate of the driven current, wind-driven current in the ocean, which will then increase the rate of ocean mixing, and in doing so, we bring the hot water, the saline water from the North Atlantic current up a lot quicker, and this increases the temperature of the surface ocean, which then causes greater loss of the sea ice as the temperature is greater, and so on and so forth. So it's really important that we try and maintain as much sea ice to prevent the speeding up of the ocean mixing. When talking about the temperature of the ocean, we need to consider the fluxes that occur. So we'll take this little section of the ocean and use it as a model. So firstly, we have the solar energy, which is the short wavelengths, and it comes from the sun, passing through the atmosphere, and then some of it is, reflected by clouds and so on. But initially, we have the QS, which is the solar energy, and that is typically about 340 watts per meter squared. Obviously, depending on the latitude and so on, that varies. Secondly, we have a black body radiation, which is the radiation emitted from the surface of the ocean, and this depends on things like the temperature, and it's related by the Stefan-Boltzmann law. Another mechanism of heat loss is the latent heat flux, and this is actually the energy lost via evaporation of water. So it's actually contributing energy to the atmosphere by doing so, but we're referring to the surface ocean for this. We then also need to consider the energy transferred from adjacent cells. So in a similar fashion that energy leaves via black body radiation, water will actually enter the system from other cells by energy being transferred in that way. We then also see that there's a thing called a sensible heat flux. Now this is the amount of heat transferred to the atmosphere by conduction due to this air-sea interface interactions. And then finally we have QT, which is just the surface, the surplus heat flux, which leaves the system. So obviously there's 4 heat loss mechanisms and then also 2 heat gains. Now we can write this as an equation, and then this is actually the ocean heat balance equation. And when this is equal to 0, each of the components of the heat gain and the heat loss are equal. We see that it's in equilibrium and there will be no change to the temperature. The ocean-atmosphere interaction. So the ocean and the atmosphere are both they have a global extension, they have a global impact, but they both share 2 fundamental qualities. The first one is that they're both layers of thin fluid on a rotating sphere. Secondly, they're stratified fluids, meaning that they have developed a density gradient due to the force of gravity. However, the ocean has a considerable effect on the atmosphere. The motion of the atmosphere, such as the winds, is actually driven from the heat from the ocean surface. And secondly, the specific heat capacity of the ocean is actually much greater than the atmosphere. And then this has a very direct control of the variability within the atmosphere. This image here just highlights the air-sea interactions that occur between the atmosphere and then different parts of the ocean and things like that. So finally, a little summary. So firstly, we learned that the Arctic has multiple circulation systems. So we have the surface ones, which are the transpolar and the Berthold Rye, and then we also have the deep ocean systems, the North Atlantic Current and the cyclonic circulation. They eventually mix. Well, they mix in a process of ocean mixing, and this is very important when considering climate change and so on. Also, the wind plays a very crucial role in providing momentum to the ocean by interactions with both the sea water and the sea ice. If we decrease the amount of sea ice, we would increase the amount of wind-driven current that occurs, speeding up the ocean mixing and also increasing the temperature more, sort of like in a feedback loop. We also considered the different fluxes that contribute to the temperature balance of the ocean surface. We looked at the ocean heat energy balance equation and all the different mechanisms that need to keep in order to maintain the equilibrium temperature. Finally, we learned that the ocean and atmosphere are both thin stratified fluids that both rotate around the Earth. And more specifically, we learned that the ocean has a very direct impact on the characteristics of the atmosphere. Thank you very much for listening to my presentation. I hope you learned something.